Hello, is my audio working? Hello, hello, hello. Is my microphone working? Because last time it didn't work. Am I live? Oh, man. Let's see. I'm going to check to see if I am live. Okay. Programmer HQ. Search filters. Live. Where am I? Am I live? Hello, can you guys hear me? I keep having problems with my audio. Okay, works now. All right, let's get started. All right, welcome back to another stream. I just woke up and straight to Leetcode. I'm gonna share my screen and get started. Share my entire screen. All right, cool. So let's see where I'm at. I'm at 20 out of 93 problems for the last 30 days. I have my mock interview with a meta engineer tomorrow. So the goal for today is at least 30 problems from this list. So let's do it. Let's get started. So I'm going to do this one, diagonal traverse 2. I'm going to start my timer. Let's go. All right, example 1. We're given a 2D integer array nums. We need to return all elements of nums in diagonal order as shown in the below images. So you go from, given this example right here, you go from 1, 4, 2, 7, 5, 3, 8, 6, 9. So 1 and then 4, 2. So from diagonally from the bottom to the top, left to right, 7, 5, 3, 8, 6, and 9. And then looking at example 2, I see that we go 1 and then 6, 2. So 1, 6, 2, and then 8, 7, 3, and then 9, 4, and then 12, 10, 5, 13, 11. So yeah, the same pattern. But I guess this case, in this issue, in this problem, what clarifying questions I would ask? The clarifying questions I would ask to the interviewer would be, so is it safe to assume that the number of elements in each row will be different? Which I believe, looking at this example, the answer will be yes. So every row will have a different number of elements. So I need to take care of that. And also, this looks like we need to keep track of each diagonal and what elements we have traversed at each diagonal. And to me, this seems like a mapping problem where basically we need to add 1 to its own diagonal traversal row, and then we need to add 4, 2 to its own diagonal traversal row, and then 7, 5, 3, and 8, 6, 9. So in our map, we need to find a way to code our key, which corresponds to a diagonal traversal row. So looking here, I'm going to walk through the traversal, cell by cell to see if I see any pattern. So we start at 0, 0 as our coordinate. Then we go to 0, 1, 0, 2, 1, 0, 1, 1, 1, 2. So I see that here it's 0, 1, and here is 1, 0, and they are in the same diagonal. Let's see if I can see a pattern for the next diagonal traversal row. So here it's 0, 2, 1, 1, and 2, 0. And what I realized is if you add 0 and 2 together here, then you get 2. If you add 1 and 1 together here, you also get 2. If you add 0 and 2 here, then you also get 2. So let's see if this is the same. So I think the x plus y can be our key for our hash map. Let's see if the example holds true here. So this is at index, let's see, row 2, column 1. So 2, 1. And this one is at 1, 2, right? Row 1, column 2. So 2, 1. 2 plus 1 is 3. 1 plus 2 is also 3. So I think we have found a pattern here. In our hash map, the key for each diagonal row would be x plus y, and basically the value would be the list of all the numbers in that diagonal row. So now I think I just gotta figure out a order of traversal. So 1, 2, 3, 4, 5, 6, 7, 8, 9. In that case, 2 will be added before 4, and then 3 will be added first, then 5, then 7, then 6 and 8, then 9, which is in the reverse order, because here we want to go from bottom to top. So I realize if we start from the last row and we go up to the last column, we should be able to, last row, and we go up to the first row, we should be able to get the order right. So here we would start at 7, and we add 7, then we add 8, then we add 9, then we add 4, then we add 5. So we have 7, 5. And then we add 6, so we have 8, 6. And then we add 1, and then we add 2, which becomes 4, 2. And finally we add 3, which is 7, 5, 3. So our order of traversal will work if we go from the bottom row to the top row. And in terms of the sparse matrix right here, I just need to check the size of nums. So the current row, I just need to check the size of that and make sure that I don't go out of bounds. So as soon as I go out of bounds, I stop. And once I have all the diagonal traversals in my map, I can just start from the key 0. So at the top, and go to key 1, then key 2, then key 3, then key 4 in this example. And once I go to a key that is no longer in the map, I know that I have finished my traversal for my int right here. And since this is Java, we need to determine how big our return array is going to be. So I'm going to keep a variable code size, set it equals to 0, and then int m is the number of rows is equals to nums.length, and then int n we don't know because every list will have a different size according to example 2. So now that I've walked through an example of how I would process my matrix, I'm going to go ahead and code it. So the first thing I need to do is declare these variables. So I also need a map integer collet. The key would be the integer, and the value would be the list of integer for that diagonal traversal. So I'm gonna call it hash map as a new hash map, just like that. And then basically, I just need to do my traversal from the bottom row to the top row. So for int I equals to basically m minus 1. I is greater than or equals to 0. I minus minus. And then here we need to get the current row. So list of integer current row is equal to basically nums get the index I. Okay. So once we have this, we just need to traverse it. So for int j equals to 0, j is less than current row size, because we know that every row will have a different number of elements. So we do a j plus plus. Okay. So let's get the current key. So int current key would be equal to I plus j, and then int current value would be equal to basically the current row at the index j. So current row will get j. So once we have this, we need to check if a list with this key already exists in our map. If not, then this will be the first time we encounter an element in this particular diagonal. So here, if we start at 7, for example, our key would be 0, 1, 2, 2, 0. So 2 plus 0 is 2. Our key is going to be 2, but we haven't encountered any element in this diagonal traversal where the key is 2. So we need to do a hash map put if absent basically current key, a new array list of type integer, just like that. Okay, and then once we have that, we just need to get that list. So hash map get this key, and then we add the current value, just like that. Okay, so once we have made it out of this loop, it means that we have populated our hash map with every single element in nums in the diagonal traversal order. So now we just need to create our result array. So RA for result array is equal to a new int of size. So size will be plus equal current row size to see how many total elements are there to be added. So we have here the size, and then we need to have a pointer. So int result index is equal to 0, because we will be traversing the hash map and populating the result index with our in order traversal. And then so now we need another one, call it m index for the map is also equals to 0, because now we need to go from key 0 to key 1 to key 2 to key 3 to key 4 and so on until we go out of bounds. So our condition for the while loop would be while m index is still in the map. So hash map contains key m index. Then what we can do is first of all get the current list. So list of integer current list is equal to hash map get m index. Okay, and after we have processed this list, so add list to result array, and then next list. So this would be map index plus plus. Okay, so now we need a for loop. So for int I equals to 0, I is less than current list size, I plus plus, and then we can do a result array at the result index is equal to basically current list get whatever is the index I, and then we need to increment result index plus plus. And finally, when we exit out of this while loop, we know that we have processed every single element, and we can just do a return result array, and that would be my solution. Let me see. We have the size, we have m, we have hash map. Yep. M start from the bottom row, going to the top. We have the current row, get the size. Yep. We process the key and the value, put it into our map. We get our result array, our result index, and map index. We increment our map index after every run. We add the current list to our result array. So this should run. We get a nums. This should be num size. Cool. I'm going to submit. Took me around 12 minutes to explain the problem, pretend to ask clarifying questions, and then finally code it. So now I would need to name the time complexity. So the time complexity of this is O of n times n, where n varies. So I'll just say that the time complexity of this is O of n, where n is the total number of elements in all the list in nums. So it will be m times whatever the biggest list is in the worst case, I guess, because we're only doing the for loop once, the double for loop once to process every single element, and then we need to process every single element to add to our result array too. So the space complexity is also O of n, where n is the total number of elements in our list nums, because we're making the hash map and our result array here. And I believe a follow-up question that they ask is, what if we go in a zigzag order? So instead of 1, 4, 2, 7, 5, 3, 8, 6, and 9, I would need to do basically 1 and then 2, 4, and then 753, and then 69 and 9. And in that case, my modification for this is basically I still start here and I go up just like that. But then when I process the list, depending on the level I'm at, if so in the case where where the map index is 0 here and we go up, we don't need to reverse our list. But in the case where it's no the map index is no longer divisible by 2, so here the map index is 1. 1 modulo 2 is 1, so we just need to reverse our for loop from end to beginning to have the zigzag order. So let me demonstrate. So if m index modulo 2 doesn't equals to 0, then we just need to copy this loop and change the indexing a little bit. I'm gonna tab this, and then this will be CL size minus 1. I is greater than or equal to 0. It would be an I minus minus. All right. And then else, we add it the regular way. So it would be like that. I guess whenever we add an element, we can just print it out to see our order of traversal. So we can just do a system out print print basically whatever we are adding. So our index and then plus a space, just like that. Do the same for here. And then I'm going to run my test case to see the output. So here it should be 1 and then 2, 4, 7, 5, 3. 1, 2, 4, 7, 5, 3, 6, 8, 9. 6, 8, 9. And then here it will be 1, 2, 6, 8, 7, 3, 4, 9. Let's see. 1, 2, 6, 8, 7, 3, 4, 9. And then 12, 10, 5. Yep. 12, 10, 5. And then 11, 13, 14, 15, 16. Yep. So this is zigzag order. And yeah, basically we just need to process every single diagonal traversal. And after that, whatever the result, whatever pattern the result want to be, we can modify each diagonal as needed. So that is my solution. Not bad. I've done this a few times. This is just reviewing, but this is a tricky problem that's been frequently asked by Meta. So, all right, next one. Least recently used cache. Let me check that. My stream is still working. Where's my stream? My stream is here. All right, I'm still streaming. All right, let's get started with the next problem. This one, least recently used cache. I'm going to start my timer. Is it asked by Meta? Let's see. Companies. A lot by Amazon, a lot by Meta. All right. We need to design a data structure that follows the constraint of a least recently used cache. Okay. So we need to implement the LRU cache class, where this one is the constructor and it's passed in a capacity, which initialize the cache with a positive size capacity. And then this is looking to see if the key is in the entry is in the cache. So the entry is like a key value pair, I'm guessing. Return the value of key. So it is a key value pair if the key exists. Otherwise, we need to return -1. Okay. And then we have another function called put, where we're adding a key value pair. So, or we're updating the value of the key if the key exists. Otherwise, we need to add the key value pair to the cache. And then if the number of keys exceeds the capacity from this operation, we need to evict the least recently used key. Okay, so we need to keep our cache a certain size as well as keep track of the order of usage of each key. So once the cache is full and we are inserting a new element, we need to find a way to find out what the last least recently used element was, remove that, and then add the new element as the most recently used element, and then update this as gets and puts a code. Okay. And another requirement is the function get and put must each run in O of one average time complexity. Okay. So if we didn't have this constraint, I'd say we just use a list, you know, of size of a list or an array of size of capacity, and whenever we call get, we just do a linear search through our int array to see if the key value pair is there. I mean a pair array. However, this would be O of n linear search time complexity. It wouldn't meet the constraint right here. And for the put, we're doing the same thing. It's O of n time complexity, where n is the number of elements in the cache, not exceeding capacity. If we do put here, we need to do a linear search and then basically update the pair once it's found, and then reshuffle the array so that whatever we just modified gets to the front. This would be very time consuming. Same with put, we need to remove the last element and then shift everything forward. However, I feel like instead of using an array, I can do a doubly linked list class, and so reshuffling the array would be O of one time complexity, because we have say we're modifying the element x, we would have access to the previous element and access to the next element. So we can just do a pointer manipulation trick, or it's not really a trick, but do pointer manipulation to remove the current element, either remove it completely if it's the least recently used element, or remove it and bring it to the front as the most recently used. Okay, so that would do our get in O of still O of n time, because we need to linearly search through the linked list. However, that would improve our put and update functionality to O of one for removing nodes and moving it to the front or moving it completely. To basically get uh, to achieve get to be O of one time complexity, I'm thinking of using a hash map where the key would be the value of the key right here, and the value would be the list node or the node that is associated with this key. So in that way, the hash map, you know, uh, time complexity for retrieving a node of a particular key would be O of one on average. So then once I have that O of one, I can just do put very easily. Like I can just look it up in the hash map to see where that node is, either update its value if that node is found, or if that node is not found, I can quickly access the last value if the size is full, remove it, then add the new input to the very front using a O of one time complexity. In order to make everything O of one, additionally, I would need to implement a tail node to access the least recently used in O of one time complexity and remove it. And then I would also need to implement a head node so that whenever a new element is inserted or a new element is used, I can quickly access the front of the list to move it to the front. All right, that was a lot of logic. Gonna walk through an example to see if I understand. So, for example, if we have our cache here and we are putting 1 1, so we have, let me just take this input and walk through this example. Okay. All right. Least recently used cache, and we are okay. So capacity equals 2. Okay, so now we're adding 1 1. So we have our head node right here, and which points to tail initially, and tail points back to head, just like that. Okay, so now we see that we're adding 1 1, and our capacity is still good. The way we can check our capacity is using our hash map. So hash map right here equals nothing, and then our list is right here. So when we add 1 1, so we would need to add this to the front. So this would be 1 1, which points to tail, just like that. Okay, so hash map now will contain the entry of 1 1 also, and now we're putting 2 2. So 2 2 comes to the front. We check to see, if 2 2 is already in the hash map. Is not, so we add it to the front. 2 2, and just like that. So now we see that the capacity is still good. And then the next one, we're doing get for the key of 1. We check our map. 1 is here. So we return our key, which is 1 1. And this is our hash map, by the way. All right, so get 1 is good. Now we do a put 3 3. Okay, so we see that our map doesn't contain 3 3, so we put 3 3. We see that now, after adding, our capacity is currently 2. And if we add another one, it will be over capacity. So we need to remove the least recently used element by accessing tail previous, which is 1 1. So we remove this by setting the previous of tail, which is 2 2, next, to be this one next. And then tail previous to be basically tail previous previous. So we're basically removing this just like that. And then we need to add 3 3 to the very front, just like that. Okay, so on and so forth. It's the same logic. Now that I've walked through an example, I'm going to go ahead and code it because this is gonna take a while. So I'm going to implement my own node class. So class node, okay. It will contain a previous reference as well as a next preference, as well as a key and a value, just like that. So the constructor public node, I guess it was just taking the key and the value, and we can set the previous and next manually. So this key equals to key, this val equals to val. Okay, now we have our class node. We would need to begin implementing our cache. So we would need a capacity to keep track. We would need, like I said, a node head as well as a node tail. We also need a map of integer to node. Call it hash map is a new hash map, just like that. And let's implement the constructor first. Okay, so we have to initialize all our variables. So capacity equals to capacity. All right, we have a head is a new list, new node of -1 and -1. And then we have tail is equal to a new node of -1 and -1. And initially head should point to tail is equal to tail. And then tail previous should point to head. And then we need to initialize our hash map, new hash map, just like that. Once we have this cache, we can begin our get function. So basically for get, we just need to check if hash map get key doesn't equals to null, then we get it. Otherwise, I believe we just return -1, -1. Okay. Then we get the node. Um, let's call it n is equal to basically hash map get key. And then before we return n value, we need to move it to front. Move to front. Okay. And then for put, basically we need to check again if the current key is in the map. If it is, then we're doing an update if present. If not present, we just move to front, create and move to front. Update and remove if present, and then create and move to front. Here, move to front. So as you see, I believe that move to front is being repeated. So I'm going to create a private helper function right here. Go private uh, to front. It will take in a node n, just like that. And then I guess before moving to front, I would need to remove, right? So another function that I think would be helpful is private remove and then node n also. And for removing, it's very simple. We just need to have the n previous, so the previous pointer, next pointer to be whatever n next is, and then set basically n next previous to be whatever uh, n previous is. So that's basically our remove function. So before remove and move to front, so I just need to remove n and then move, call it to front n, and then return n value. Similarly, I'm just going to copy this logic. If the thing, the key value pair is already present, then we remove it. Create and move to front. Do I need to update it in the hash map is my question. So remove, and then I need a node. N is a new list node of key and then value, and then to front. I don't need to remove it because it's a brand new node, and then move to front just like that, I believe. Oh, I forgot one case where the capacity is too big. So if the capacity, right? If else if right here, the capacity is now over capacity, hash map size um, is greater than or already equal to capacity, then remove the least recently used. So remove uh, tail previous from both the hash map and the list. So hash map remove tail previous value. And then we can begin creating our new node and then add it to the very front. So now I just need to implement the to front function. So we have our node n. So we need to set n next is equal to head next. Okay. And then head next previous is equal to n. Okay. And then, so say we have like this head and then 1, right? And then we are inserting 2. Okay. So this one is n equals 2. Okay. So now head next. So we need to do a 2 right here, just like that. 2 next is also equals to 1. And then head next previous. So, well, okay. This has to come before then. So going back to our example, okay, head right here, next right here. previous has to be equals to n, which is 2, just like that, okay? And then n next is equal to head next, just like that. Good. So now we need to modify n previous is equal to head. So making this link. And then we need to do a head next now is equal to n. And I believe this should move the node to the front. So head next previous is equal to n. Yep. N next is equals to head next. Okay. And then n previous is head, and then head next equals to n. So this solution should work. Return type is required. Private, it will be a void function. And private, this also would need to be a void function. Remove basically hash map get key. Oh, create and move to front. Well, we need to get it and then move it to the front, as well as add it to the map. So it would be a hash map add basically key and then n. So we are removing it. What if, and then making a new node with the new key and the value and add it to the front. If the size is over capacity, then we remove it from the tail, make the new node anyways. If it's not over capacity, yeah, this should work. Hash map, this would be put accepted, run it, and we get a wrong answer right here. So there is a bug somewhere. Let's see. I think if I update the put function, let's see the get. If the key is present, we get the key, we remove it, and then we add to the front, and then you return. Okay. Otherwise, if the key is present, shut up. If the key is present, we get the key, we remove it, and we create a new one, update the map, and add it to the front. However, if the key is not present and we are over capacity, right, then we remove from the map, and then we remove from the tail, and then we make the new node, add it to the front, add it to the map, and add it to the front. Yeah, so I'm not sure what my my bug is here. So let's ask ChatGPT. Where is my bug in LRU? My put method. Oh, I'm removing using the value instead of the key. Yeah, remove. This should be the key. So then if I use this test case and I run my code, yeah, it's accepted. So cool. Small hiccup. I'm removing. So the logic was right. I'm just removing the wrong thing. I'm removing I was removing the value instead of the key. But basically, the time complexity of this is, I believe it meets the constraints of O of 1 in average. So as you guys can see, get, we just look up the node in the hash map, and return the value in the hash map. So that's a O of 1 time complexity. And then for put, you can get in constant time O of 1 by using our hash map and then removing. Since it's a doubly linked list, we have access to the previous pointer and the next pointer, which is O of 1, removal and addition to the front. So yeah, meet the constraint. I think I'm getting a call from somebody. So I'm going to mute myself